Hello. Today we're going to talk about the Carnot cycle. So it's based on Carnot's principle. So Sadi Carnot, he was a French scientist and engineer. He was born in 1796, died in 1832 at the age of only 36 years old. He died of cholera, unfortunately. He discovered this interesting result that's a consequence of the second law of thermodynamics. That's the one that relates to entropy. Entropy never decreases in the universe, basically, and in general will increase, or in a reversible process will stay the same. In any event, even in an ideal situation, the efficiency of a heat engine depends on the temperatures between which the engine operates. So what is a heat engine? A heat engine is a device like a gasoline engine you'd find in a car that uses heat to do work. So what it comes down to is that you cannot have a 100% efficient engine. Even in an ideal case, you cannot get to 100% efficiency. So Carnot came up with this idea, this equation in fact, that the ratio of the heat sort of dumped from the engine at low temperature divided by the heat you get out of the engine at high temperature, say by burning gasoline, is proportional to the absolute temperatures, the ratio of the absolute temperatures between which the engine operates. And we'll call those T low and T high. And this has a corresponding efficiency equation, which we call the ideal or Carnot efficiency, which is that the efficiency, the Carnot efficiency, is 1 minus this ratio of temperatures, the low temperature divided by the high temperature. So you can see that's very important if you want to maximize the work you get out of a particular amount of heat from your engine. It's very important to have a low temperature at which you dump the sort of waste heat from the engine and a very high temperature. So for instance, this is why a diesel engine is very, very efficient, because the temperature inside the diesel engine is much higher than in a regular gasoline engine. Okay, but even basically you'd have to go to absolute zero for your low temperature to get a 100% efficient engine, and that's just not possible. So let's look at the Carnot cycle in some detail. So it's a four-step process. So the first step is an isothermal expansion at what we'll call T high, and this involves some amount of heat going into the engine, so for instance maybe by burning gasoline or diesel fuel or something like that. And we'll put that in so it goes in with a positive sign. And then we also have a change in entropy. And change in entropy can be determined by the heat divided by the temperature at which that heat is added or subtracted. So in this case, nice simple calculation, QH over TH, because TH is a constant value because we're doing it isothermally at constant temperature. Second process is an adiabatic expansion. And we'll expand the system adiabatically to a lower temperature TL. So in an adiabatic expansion, by definition, there is no heat involved. And if there's no heat involved, there's also no change in entropy for that process. Then we do another isothermal process. This is a compression at this lower temperature TL. And to do that, that requires extracting heat from the engine. So QL, there is a negative number. And again, our change in entropy is a nice, easy number to calculate. It's the QL divided by the TL, and that, of course, is a negative quantity because QL itself is negative. Then finally, we do another adiabatic process. This is an adiabatic compression to the high temperature, the original high temperature. This brings us back, in fact, to the original state of the engine before step one. Again, no heat's involved because that's adiabatic, and there's no change in entropy. Okay, so the whole cycle, we've got a net amount of heat, QH plus QL. Again, remember that QL is a negative quantity. And that's some positive overall thing. QH is bigger than QL. So QH plus QL, where QL is negative, is a positive quantity, but delta S, in fact, is 0. And that's simply because we're really back to the same entropy value when we return the system to its state that it had before step 1. Okay, so overall there's been no change in entropy for the complete cycle. Okay, so we go around a complete cycle, we're back to the original pressure, the original volume, the original temperature, and the original entropy. So there's no delta S for a complete cycle. And this is what leads to Carnot's expression. QH over TH is going to be equal to minus QL over TL, in fact, and in Sadie Carnot's expression, his QLs were just the magnitudes. Okay, so if you in fact plot that cycle on a PV diagram, you should try that in fact. Plot that isothermal expansion followed by an adiabatic expansion followed by an isothermal compression followed by an adiabatic compression that returns the system to the original state. It's a funny shape on the PV diagram. Okay, so we're going to do a different diagram, and it can be helpful to think about this in thinking about the second law, or even for heat engines. We're going to draw not a PV diagram, but a temperature entropy diagram. And the nice thing about the Carnot cycle is that temperature entropy, T for temperature, S for entropy, diagram is nice and simple. So here we are plotting temperature, again it's absolute temperature in Kelvin on the vertical axis, and entropy in joules per Kelvin, pardon me, on the horizontal axis. And our engine operates between these two temperatures, T high and T low, and it in fact operates between two values of entropy, we'll call S1 and S2. So we'll start at the top left corner of the cycle, and we'll do our isothermal expansion, and that moves the system from entropy S1 to S2, but it keeps the temperature constant there. Then we'll do an adiabatic expansion. So there's our adiabatic process, and that keeps the entropy the same, lowers the temperature. We'll do another isothermal process, that's an isothermal compression, and that actually brings the system back to its original entropy S1 at a constant temperature TL, and then we do a final adiabatic compression, and again it's adiabatic, so there's no heat involved, there's no change in entropy involved, and we're back to the original state with the original pressure, volume, temperature, and entropy. Yeah, there's an adiabatic compression there, that last one we did. So it's a really nice, simple shape on the TS diagram, whereas you get this very odd shape on the PV diagram. So let's think about what the area under the curve represents here on the TS diagram. So remember, on the PV diagram, the area under the curve is the work. So what units do we have here? So if we multiply temperature by entropy, we get kelvins times joules per Kelvin, so we're left with joules. So the thing that's the area under the curve does have units of energy. Another clue to what this is that for the adiabatic process, if you take the area under the curve, it's 0. Okay, and of course Q, the heat, is 0 for an adiabatic process. So that, in fact, is what the area under the curve represents on the TS diagram. So that first isothermal expansion at the top, that represents QH, the total area under the curve there. And then coming back in that third step, that bottom isothermal compression, you get a negative quantity under the curve, and that represents QL, the heat that you have to eliminate from the engine at the low temperature. And then you've got this area inside the rectangle on the TS diagram, and that's the net heat added to the system in the process, because QH is bigger in magnitude than QL. Okay, So that's a pretty good introduction to the Carnot cycle. And nice thing about the Carnot cycle is that it's reversible. It is basically it's not 100% efficient as we talked about, but it's the most efficient engine you can have operating between temperatures of TL and TH.